Questions about that? Okay, excellent. You're going to have a quiz over the weekend, and it will be over something in this chapter that we get to before the weekend. I feel we are going to cover this chapter 14. Whatever, the chapter on inductance.
Oh,
yes. And yeah, in lab we're doing a little Mathematica. It'll be a little fun because I expect there'll still be some typos in the lab because I wrote it up last weekend. But by Thursday, I bet everyone else will have. So if you have like a later lab this week, it's better. But yeah, it's a nice little lab. Probably very useful for people. Okay, so finishing chapter 14 this week. Peer reviews due this Friday. Quiz over the weekend. Expert TA due Friday. Next week you're off. Everyone pretty solid. Okay, anything we need to talk about besides physics? Okay, let's do some physics then. Everything set. I'm recording. I've got my. Okay, cool. We're doing inductance, and I feel we got a fairly solid start on it last week. Where in general, like an inductor is just a coil of wire, and because when you send current through a coil of wire, it creates a magnetic field. It has this like self-inductance thing where by Faraday's law, it makes its own magnetic flux across itself, and then it tries to stop that magnetic flux that it just made. So we decided to call just like the definition of inductance this L, where when you sent a current through a wire that might even have a time dependence, L was the factor that converted that changing current into a voltage. We got a general equation for inductance, number of coils in whatever system, magnetic flux in the system divided by current, which was in henries. And then we calculated the inductance of a solenoid, which is going to come back again and again, where the inductance of a solenoid was permittivity of free space. And of course, if you have like an iron core solenoid, that would be the permittivity of iron times the turn density of the solenoid squared. And turn density, remember, number of turns over unit length, multiplied by the volume encased in the solenoid. So like the cylindrical volume inside of the solenoid. Okay. And the first thing we're going to use this for is we're going to talk about energy in a magnetic field, where I want you to kind of think back to capacitors, where the really standard capacitor picture that we drew was two parallel plates, because that was a really straightforward kind of example. And we said, well, inside of these plates, there is an electric field going from the positive plate to the negative plate. And we use the definition of capacitance to get to that. But then even more than that, we said, okay, there is a volume of like a cubic volume inside of that parallel plate capacitor. And so at that point, we're able to relate the energy density of an electric field, energy per unit volume, to the electric field magnitude that it took up. But basically what we did here was we said, okay, I can tell you how much energy is in a capacitor. So we said, okay, I have the energy of a capacitor, Q squared over 2C, that we had derived earlier from thinking about just how a capacitor works in a circuit. And then we said, okay, where is that energy coming from? Like where is it being stored? What form of energy is that? And we said, well, the energy in that capacitor is really being stored in that electric field. That's what has the energy in it. It's the electric field. So we just said that this energy was equal to the electric field energy, and then we were able to divide out the volume of that capacitor, and that's how we end up with that equation. Okay, vaguely familiar? We're going to go through the same process for a magnetic field. And we're going to use solenoids to talk about it because we have this relationship. We know how a solenoid makes a magnetic field. So we know that the magnetic field in a solenoid is mu naught Ni. And we have some idea, and we will, there's going to be some math here. We have some idea of how this solenoid, which is an inductor, is going to act when you hook it up to a circuit. And so we're going to use that to figure out the energy inside the solenoid, and then we're going to say, okay, well, that energy inside of that solenoid comes from the fact that it's generating a magnetic field. And then we're going to say, okay, I have the inductance of a solenoid with respect to volume. So we'll be able to get an energy density of a solenoid, which will hopefully depend on a magnetic field. Everyone kind of okay here? Okay, cool. Let's set up our problem then. Okay, so we are going to go through a really standard circuit here. And we're actually going to be doing this problem many times today. But I have a battery with some EMF. I have a resistor, and I have this inductor, which is really some sort of solenoid. If I were going to draw a picture of just that, it'd just be some cylinder with wires wrapped around it, like so, that makes a magnetic field, whichever way the current's going. How do I have the current going here? I have it going that way. I have it going, oh, I wrapped it the wrong way. But anyway, I have my current going that way, so I'm making a magnetic field like that, right? Where the magnetic field is pretty much contained inside this solenoid that has some sort of volume. Okay, excellent. So what I would like to know is, since this magnetic field, it has energy in it, I would like to think about if I could get an equation for the energy that's going into that solenoid. So far, so good. Okay. So let's first talk about what's this circuit's going to act like. So let me put a switch in here. Okay, so I have my switch. At time equals 0, my switch closes, right? And current wants to start going around this circuit. But then current's going to hit this inductor. And what's going to happen then? Maybe something in terms of a magnetic field? Okay, so it's going to create a magnetic field. What's that going to tell you about the magnetic flux? Before I had any current, do I have any magnetic flux? When I do have current, do I have magnetic flux? Okay, so I've all of a sudden gotten this magnetic flux. Does the inductor like that the magnetic flux suddenly changed across it? No. So initially, when this circuit turns on, this inductor is going to look like a battery that opposes any current coming in. It's going to generate an EMF due to that flux changing. And in that way, it's actually going to block the current for a short amount of time because it's acting like a battery that opposes the other battery. But will it be able to keep producing this voltage? No, right? Because this is a time-dependent thing where the longer something goes on, the less voltage you're going to see out of it. So basically, you flip this switch. So you flip this switch right here. Current wants to start going, but it's initially blocked. But then over time, it's this EMF goes to 0, and so then current starts flowing like this inductor isn't even there. Although it does definitely have that magnetic field. And basically what's going on is initially the energy that you would put into pushing current around that circuit goes into creating this magnetic field. Make sense? So it's not coming from somewhere. It's coming specifically from the other battery. Okay. Let's start writing down equations that we could maybe do something with. I have a circuit that is one loop. Is there an equation that you might think of writing down when you have a closed loop of circuits? Say again? Kirchhoff's loop. Because not because I desperately need to know the current, but because I know it's true, at least. I know I can add up all the voltages through that circuit and they'll add up to 0. So let's start there. So I'm gonna go around this circuit like that. I'm gonna set my current to go that way. As I go across this battery from negative to positive, am I gonna add that voltage or subtract it? Yes. Yeah, so is my voltage, I'm going from the 0 volts to the 6 volts, right? Yeah, so we're adding this voltage. So I'm adding my battery. I'm going with the current across the resistor. Am I going to add or subtract that voltage? You subtract that voltage. And then let me tell you, as you go across the inductor, you're subtracting that voltage as well. And then you're back to where you started, so that all needs to add up to 0. Okay. Now, what I know, because I have my notes in front of me, is that I could use power to talk about this. And the way I'm going here is I know that power equals current times voltage. And I also know that power is the time derivative of energy. Right? Power is the rate of change of energy. So one, I have a bunch of voltages. If I multiply by a current, I have power. So like I know I can get to power. And then I know that through power, I can get to energy. So that's where I'm going with this. So let's multiply through by just whatever current's going through my circuit. So I have current times, this is the battery voltage. I'm going to put everything else on the other side of this just so I have it. I have current times the resistor voltage plus current times the inductor voltage. Okay. Over here, this is the power from the battery. So the power coming out of the battery is just whatever current it's supplying at the voltage that's set at. For this voltage across the resistor, I know that voltage across the resistor is just IR. So I know that just by Ohm's law, that's true. And if I'm multiplying this IR times another I get I squared R. I don't suppose that reminds y'all of anything. Okay. That should remind you of another equation for power. Remember, we had three equations for power. IV, which was what we usually used for the battery. Then we had I squared R, and that's what we use for power dissipated by a resistor. So, or energy dissipated by a resistor. So this is the power, basically the energy that the resistor is dumping out of the circuit. And then we have this last term, which I know the voltage across the resistor. I'm sorry, I know the voltage across the inductor. That's L di dt. And really all I'm doing that is I'm just taking L di dt. I'm just taking that and I'm multiplying it by another I. I did drop the minus sign because I actually, that's the minus sign right there. Makes sense? Okay, so for this last term, I have L I di dt. Okay. Now this last term, that's the one that's kind of interesting to us. Because, so the battery is putting energy into the circuit. And when it puts energy into the circuit, the energy can go one of two places. It can be dissipated by my resistor, or it can be used by my inductor to make a magnetic field. So if I want to talk about how much energy goes into making a magnetic field, I talk about how much power that inductor is eating up. Does that sound reasonable? Okay, cool. Excellent. So the power that inductor is eating up is really how much energy is the derivative of the energy of the magnetic field. So how much energy you have to keep putting into that magnetic field, which, by the way, we're going to start talking about the energy in the magnetic field by using a U. Just kind of like when we're talking about the electric field, the energy in the electric field, we started calling that a U. Basically, because you might think of it as a potential energy, an energy that has the potential to cause electrons to gain kinetic energy. Okay, let's do a both sides here. My inductor power is I L di dt. That equals dub dt. But I didn't want the power of the magnetic field. I wanted just the energy in the magnetic field. And so if I want to get rid of that time derivative, I will integrate with respect to time. And so on one side, it's pretty straightforward. On one side, I have the integral of a derivative. And when you take so if I'm taking the time derivative of the energy, and then I'm integrating that, what am I going to be left over with? Yeah, just energy, right? The integration and the derivatives cancel. I just have that. And that should be a capital B. I don't know why I've been writing it as a lowercase. Okay, on the other side, I have a few things happening. But so let's write this out, and then let's talk about constants and variables and what we want to do. Okay, so I'm going to treat this one slightly. Yeah, let's treat this slightly different than the first. Where I'm gonna kind of cancel those dt's out, which you can do because I'm kind of doing the same thing. I'm canceling out the integral and the derivative there. Next, that capital L, the inductance. Would you consider that a variable or a constant? Constant. I like it because it's a solenoid, right? Whatever it is, it's not changing. Okay, then I'm integrating I with respect to I. And what is the integral of I with respect to I? Yeah.
I squared.
Yes, 1/2 I squared, right? Yeah, you had it. 1/2 OI squared. Okay, this is good. So here's our first answer. If you have some solenoid, some inductor, some coil of wire, and you put a current through it, the energy in the magnetic field that will be generated is this 1/2 Li squared. What sort of units do you think that's going to be in? We're in energy now, but joules. Power would be watts. Okay, so that's the energy in a magnetic field if you have an inductor. But even more than that, we went through all this solenoid stuff, and so now I want to play the game where I know that the inductance of a solenoid is mu naught permittivity of free space turn density squared times the volume inside of that solenoid. And so I'm going to take that and I'm going to plug that in to the L right there. Okay, so that means that I have a magnetic field energy that's equal to this. And that's not very satisfying. But wait, there's more. Because I also know the magnetic field of a solenoid. So once again, as long as we're sticking to our solenoids, what is the magnetic field of a solenoid? Mu naught in I. And I see I'm kind of close to that, right? Because I have a mu naught in I, and then I have another in I, and I have a volume at the end of that. And if I just had another mu naught, this would be really nice. And so why not? I'll put a mu naught right there. I'll put a mu naught right there. So I'm just multiplying by 1. That's allowed. And so now there's 1B field of a solenoid. There's another B field of a solenoid. So I have a B squared. So this is 1 over 2 mu naught B squared times the volume of whatever solenoid we're talking about. And you notice we're really close to what we had before, where I'm going to divide both sides by the volume here. And I'm going to get my energy density. Energy density of B squared over 2 mu naught. This is in joules per meter cubed. Okay. Mathematically, I made several substitutions there. Is it sensible? No one's screaming. Okay. If this is sensible, one thing I would like to have you compare this to is the energy density of an electric field, which, as you remember, is epsilon naught over 2 times the magnitude of an electric field squared. And we'd like to just kind of look at that and say, these are pretty similar equations, right? I have a 1/2 in both of them. I'm taking the magnitude of the field squared in both of them. And then I have this permittivity and I have this permeability. And both of those constants really talk about how easy or hard it is to get the field into the space that you're talking about. So they both mean the same thing. And this is gonna come back around when we are looking at chapter 16 when we talk about electromagnetic waves. And we say, well, this like electric field and this magnetic field, they're really like two sides of the same coin. They're doing the same thing. And that's why EM is so nice, because it's electromagnetism. It's not just that you can write down equations with both of them, it's that they literally are manufactured by the same mechanisms. Does that kind of make sense? Okay, cool. All right. We're going to keep, which equations do I need to circle? Keep this one on the top of your head. That one's going to come back a whole lot. This guy, wait 2 weeks, wait 3 weeks, and it's gonna where that's kind of where we're going to end the semester at. So far, so good? And if that's good, I want to go back to this picture, and I want to talk about this current. Because we kind of talked about it. We said, okay, well, first, this when you flip the switch, this inductor is going to try to block the current, but then as time progresses, its ability to block the current will decrease, and so the current will increase until it hits like a steady state over a long time. And now I'd actually like to find an equation for that current. And so let's set that up. We're going to do RL circuits. RL circuits. And do you guys remember RC circuits by any chance? Circuit, yeah, the with the resistor and capacitor where you charged up your capacitor and then you discharged it. Okay, excellent. This is somewhat similar, where we're going to get kind of the same equations. There are kind of a few differences, but let's go through this. Okay, so I have my circuit, and we are going to charge my circuit first, where if you want to charge your circuit, you hook up your switch to A, so your battery is in the circuit. So if you're hooked up to A, you just have the battery, the resistor, and the inductor. And that is what we had earlier, right? Just battery, resistor, inductor. Okay. I would like to find the current through this thing with respect to time. Do you want to find anything else? Just the current? Yeah, that's just the current. Okay, I just want to find the current with respect to time. And let's kind of go through what we expect to see. So time equals 0, we close the switch to A. Initially, what do you expect the current to be?
Yeah.
0, good, because yeah, you flip that switch closed, your inductor makes this EMF that tries to block it. So initially we expect 0. But as you told me, over a long period of time, the inductor can't sustain that voltage. So after a while, it drops any voltage whatsoever. So after a long time, what would you expect the current to become?
Would it just be the drop off of like?
Just like across the resistor?
Yeah.
Yeah, exactly right. So yeah, after a long time, if the inductor's not really doing anything, the resistor is the only thing blocking the current. So we're back to just like what this circuit would look like if you just had a battery and a resistor. Okay, so if I were to draw this current with respect to time, I would know that I needed to start down here. I needed to end up here after some long time. What sort of graph would you expect this to be? For example, would you expect it to be linear? I like the no. Okay. Would you expect it to look like that?
I was thinking more like a sine wave because I'm not the drops like down.
Oh, that's actually.
If not over that.
How do you feel about that guy? Okay. So yeah, I like that. You're definitely no linear things going on here. The sine graph's actually we're actually going to get a sine graph later on when we start adding a capacitor to this. So you're not just charging it, but you're discharging as well at the same time. And I don't like the red because that leaves you with a discontinuity, and we don't like discontinuities. So we're right there, and I'm hoping you guys are looking at this and you're saying don't know exactly what that is, but it's like a 1 minus e to the negative at, where there'll be some constants in there, like a will be some constant. We'll multiply it by some other constant, but it's going to look like this because that's what this graph looks like. Okay, this is great. Finding current. We conceptually know what it looks like. We need to write down an equation, and we already did. That's kind of the beautiful parts. There's our equation. We related everything in the circuit. We have something here. I am not going to multiply this by I the second time, but this is definitely where we're going to start. And we are going to substitute that in for the voltage across the resistor, and we'll substitute that in for the voltage across the capacitor. Okay, so we're starting at this point. Excellent. Where the voltage across the resistor is just IR, and the voltage across the inductor is L didt, just by definition. That was the definition of our inductance. Okay, this actually isn't that bad because right now we have our battery voltage constant, resistor constant, L constant, and everything else is in terms of I and T. And so it's all T in a format that's pretty nice. All we have to do is separate it now, get all our I's on one side, get all our T's on the other. You guys might be bored by this at this point because you've solved this differential equation several times. One could think. So just going through some algebraic steps. I'll divide both sides by the resistance. E over R minus I minus L over R di dt equals 0. I'm going to move this to the other side. So I have negative L over R di dt equals I minus battery divided by resistance. And then last step, no, not really last step, two last steps. I will divide both sides by this guy, and I will multiply both sides by the dt and the negative R over L. So basically, I'll take all of this and move it to the other side, and I'll take all of this and move that to the other side. Does that make sense?
Why do you, so you move the something to the right, then you're moving it back to the left?
I'm going to divide it out. So yeah, mainly I wanted to flip that minus sign, and then I'm going to divide it out. So I'll have all my I's on one side and all my T's on the other. Okay, so that's going to look like di over I minus that, and then the other side is going to be minus R over L dt. Okay, and we will integrate both sides. So I'm integrating di I minus battery over resistor, and I'm integrating R over L dt. Okay, this looks good. And let's put some limits on this. So I'm going to start my time. When should I start my time?
0.
0, solid. What's my current at time equals 0? 0 as well. Okay. I'm going to end up at some time t, and whatever that current is, it corresponds to the current at that time t. Sound good? Okay. Right-hand side. What is the the capital R, capital L? Those are constants. So I have negative R over L integral of dt. And what is the integral of dt? T, like it. So I have t minus 0. So I have negative R over L times t. Okay, left-hand side. Not as pretty. How would you guys approach this integral?
Are you able to pull out the E over R since it's constant?
I can't because it's part of that fraction.
Can't you pull out 1 over here? Yeah, can't you pull out R over here?
So if I multiplied both, like if I was like, okay, what if I like maybe multiply this whole thing by E over R, right? So I could, what that would give me is that would give me a R over E minus 1 like that, right? Yeah, it's entangled. You can't pull it out. But you're right. That is the problem right there. Any other?
Multiply it by its reciprocal to get the top, and then draw the dimension.
Trying to complete the square. Maybe make some sort of substitution.
U substitution.
You got it. Okay, here we go. U substitution, where I minus e over r will be my u. And so what will my du become? Di. Excellent. Yeah, so whenever you have like an awkward constant running around, that's a good first choice. So I have du over u. Integral of du over u. Say again? It is a natural log, right? And we're happy to see the natural log show up because we know we need an exponential at some point. So it's the natural log of u. We'll plug back in what our u is because I really don't want this in terms of u. I want it in terms of I. And we'll remember that our limits start at 0 and go to I. So the natural log of I minus that minus the natural log of 0 minus that. You guys are then going to tell me that the natural log of A minus the natural log of B equals the natural log of A over B. A over B. I'm going to make sure I put my minus signs in the right place. I think I did. Yes, I did. Good for me. Okay, so that's the left-hand side. So we will take this. We will set it equal to this. We'll solve and put I on one side and everything else on the other, and we'll have our equation. Okay, so I have the natural log of I minus that over negative that. That is equal to this. How are we getting rid of that natural log? Little e, excellent. Which, that's where I am on that side. And over here we have this nice decaying exponential, which is good. We'll multiply both sides by that denominator. Sorry, just another few lines of algebra. We're almost there. And then we will add that to both sides, making this the voltage, the battery voltage divided by the resistor minus the battery voltage over the resistor, e to the negative R over L times time. And let's write that as a battery voltage. That's battery over resistor, 1 minus e to the negative t over tau, where this tau is L over R. Okay. Algebraically, are we okay? Conceptually, does this match what we had back here? Excellent. It needs to, and it does. We have this 1 minus e. We have 1 minus this decaying exponential, where we found out that A And we wrote it as like 1 over A equals L over R. Where I'm kind of hoping the reason that we put it in that exact format is, if you remember, for the capacitor, we had a really similar thing, and we had T over tau for that one. And so we just want to keep that format for ease of use. We notice that when we plug in T equals 0, we end up with 0, right? And when we plug in T equals infinity, we end up with battery voltage divided by resistance. So not only does this work out conceptually, this hits like everything we needed it to hit. Sound okay? Okay. So this is my RL circuit charging RL circuit. Let me ask you a question. So for a capacitor, for an RC circuit, we charged it like that. And so, yeah, we hooked it up to charge it. And then we unhooked it. When you unhook an RC circuit, does your capacitor stay charged? Does it store the charge? Or is it not holding on to anything? You want it to hold on to things? Yes, you do. Because you want your capacitor to store the energy, right? I'm sorry, I lost that.
You said that you're unhooking it?
Yeah.
Yeah, so like get rid of the energy, or would it eventually get rid of the energy?
For the capacitor, it won't. So because the capacitor, it's got those pluses and minuses. And once you unhook it, like even if you take that capacitor out, it still has the charge. But what about this inductor? Because the energy in this inductor, it's not holding on to charge. It just has a current that makes a magnetic field, right? When you unhook that from a battery, and think about like literally, I have a coil of wire. I take away the battery. Is it going to keep making a magnetic field? No. So can it store the energy for later? Excellent, perfect. Okay, so this inductor is really good at momentarily holding the energy. So while it's actively in the circuit, it can hold on to that energy. But it doesn't independently store energy. So a capacitor is pretty unique in that it will store the energy. You can put energy in a capacitor and hold it for later. But this does not do that. All it's doing is reacting to what else is happening in the circuit. Sound okay? Okay. Now I'm gonna do like a short version of discharging because I feel we have done this. If you wanted to discharge the circuit, of course, you would, where am I? You would take this and you hook it up to B, right? So you go straight from A to B, and you do it quickly. And then that would give the inductor somewhere to discharge across. Does that make sense? This isn't something that you usually do, just so you know, because generally you're going to lose that magnetic field so quickly that you're really not going to be able to discharge any energy. This isn't a thing that really happens. Well, we'll talk about where this will happen. Where if you manage to have this fully charged inductor and you hook it up very, very quickly to a resistor, at that point, this inductor that had some current going across it, all of a sudden doesn't have current going across it. What will it want to do? Will it want to keep a magnetic field as it had it, or will it be happy to have that magnetic field change? It wants to keep it because inductors do not like change, right? They want things to stay the same. So if you manage to switch this fast enough, this inductor will try to send out a current. It will generate an EMF, like so, in the opposite direction as it did before, because now instead of trying to stop the current, it's trying to support the current. And so, and if you give it somewhere to hook up, that's where you're going to see this current flowing. Does that make sense? Where initially you will want to see the exact same current that you had the moment before. After a long amount of time, what would you expect to see? I hope you said 0 in the back there, right? Because you can't generate this current infinitely. At some, you're going to run out of energy, right? That inductor only has so much energy to work on. So that's exactly where you're going to end up, where we would expect the graph of this start up here to end down here to look like that. And if that makes sense, what sort of function looks like that? No, but you're in the right ballpark. Where you're,
It's not negative, right?
it's positive. It's instead of 1 minus E, it's just E, right? Where this is like just the decaying exponential. And if you go through the math, that is exactly what you end up with. I'm just going to write it down. Where discharging, you get that. Where tau again is L over R. Everyone kind of happy with this? Okay. I'm not going to go to the next. I'm going to stop and do some problems. But I do want to just mention the next section for Thursday, where these time constants tend to be very small. Like milliseconds is a big time constant, actually. So the idea that you would manually, with your hand or even like a button, flip the switch and be able to get any energy off that inductor is not really a reasonable assumption. But what you will be able to do is if you see fluctuations in your circuit, that's when your inductor gets really useful. So if the signal coming into your inductor bounces around a little bit, the inductor will automatically try to block off the highs and then try to support the lows. And so you might see an inductor do lots of things if you have a circuit where your voltage alternates. Make sense? Hint, hint. Whatever. It's also kind of nice if you want like a surge protector. So like you have your computer hooked up into the wall, lightning hits your house. Your computer all of a sudden has a huge amount of current going to it, right? Inductors will block that just naturally because that's what they do. They see a change in current and they try to block it. So that's maybe the more intuitive version of that. Okay. Okay. Let's take this. Let's do some problems because I have there's a lot of problems in here that I would like to look at. Where do I need to be? Where's my? There, not so much. Sorry, trying to get back to the problems I want to do. 15 is that? No. So I want to do the two ones with the inductors in series and parallel, because those are kind of nice to think about, which are apparently way back in the beginning of the chapter. There's my okay, there they are, finally. Okay, inductors in series and parallel. Because of course you might have more than one inductor, and you might need to think about how inductors work in series and get like an equivalent inductance, and same thing for inductors in parallel. So number 4 and 5 have to do with finding equivalent inductances, just like we did for capacitors and just like we did for resistors. So let's look at this. Say I have a circuit where I have two inductors, and we're going to start out in series. Okay, so I have L1 and L2. I am measuring the voltage across each of these things, and I have an ammeter set up so I can tell you about the current as well. I also have a voltmeter that reads off the voltage across both of them together. We're going to call that the equivalent voltage, because that's the voltage we would get if we hooked up an equivalent inductor. Sound okay? Now, looking at V1, V2, and the equivalent voltage, I'd like to write down an equation that uses all three of these things. And there's only going to be two different answers to that. Either we're going to add the voltages together to get the equivalent voltage, or all the voltages will be the same. So, do you think that we should add the voltages together, or do you think that all the voltages are the same? You'd add them together. And how do you know that? Right, so whatever voltage across here is, we know Kirchhoff's law says that the voltage across here plus the voltage across here needs to be equal to the total voltage. Okay, I like that. Excellent. Excellent. Let me erase some of the multiple lines I've drawn now. Okay. Okay. Now let me ask you about the current, where I have the current through inductor 1, I have the current through inductor 2, and I have the equivalent current that would go through this equivalent inductor. And same question, are we going to add these two things together to get the equivalent, or are they all going to be equal to each other? What do you think? Well, for me, let me just go ahead and ask you this. If I have resistor 1 there and resistor 2 there, and say the current through the battery there, I don't even need the current through the battery. What can you tell me about the current through 1 versus the current through 2? Say again? They need to be equal to each other, right? And that's not necessarily because those things are resistors, it's because they're all on the same wire. So it's not that you could have like 10 electrons going through there and only have 9 electrons going through there. If 10 electrons go through one, 10 electrons go through the other. So given that, do you think these currents are equal, or do you think you need to add them up? They should be equal. Awesome, awesome. Okay, so now we have these two equations to work with. What I want at the end is I want L equivalent equals L1 and L2 in some format. It'll either be L1 plus L2 or it'll be like 1 over L1 plus 1 over L2. So let's start here. Do we have an equation that links inductance to voltage? Gosh, I'm hoping someone says yes. Maybe we got it right there, right? Because we have the voltage equals L di dt. So let's write that down. So I have the voltage of 1 equals L1 di dt. Voltage of L, sorry, that's not Li, that's L1. L2 di dt equals the equivalent inductance, di dt. Now I'm going to ask you two things about these. I don't know what I'm going to ask you about these currents yet, but I don't have currents. I have derivatives of currents, and let's talk about if that matters or not. Because I could be in one of two states. I could be in like a steady state, like I could have turned this guy on a long time ago, and it could be running at some steady state, you know, fully charged up, whatever. And if it was fully charged up, I'd hit this portion of the graph over here. What could you tell me about DIDTs? But yeah, so it's not changing. Those would be 0. Wouldn't be a very interesting, because it's not changing, the derivative would be 0. So not super interesting. But what about if you're on any other spot on that curve? And what I want to ask you there is, clearly this thing is changing. It's got a DIDT to it. But if we look at the DIDT here versus the DIDT there, would they have to be the same, or could they possibly be different? They have to be the same, right? Because if they start at the same current, which they do, they start at 0, and they change a different way, that means at some later time there'll be different currents. And you guys told me that couldn't happen. If 10 electrons go through one, 10 electrons are going through the other. So when we said that their currents were the same, not only are the magnitudes of their currents the same, the derivatives of their currents are the same as well. Does that make sense? Okay, so we could just cancel those out. And we can end up with a very, very solid equivalent. What are we? Inductance is just adding up the inductors. So this is inductors in series. Sound okay? Is this similar to the way you add up capacitors in series, or is this similar to the way you add up resistors in series? Resistors, yes, way to remember that. So for resistors, if they're in series, you just add them up, right? For capacitors, you have to do that 1 over, 1 over, 1 over. And so you should definitely expect that when you add up inductors in parallel, they will add like resistors in parallel. So we expect to see 1 over L equivalent equals 1 over L1 plus 1 over L2. And let's do that. Which brings us to number 5, where we have two inductors in parallel, L1, L2, and we are of course comparing that to an equivalent inductor that does all the same stuff. Okay, and so we are going to go through the same questions. Do we want to say their voltages are equal, or do we want to add up their voltages? So if you look at the voltage across L2 and the voltage across L1, would those add up to some equivalent voltage, or would you expect them to be just the same? I like equal, right? Because they're all hooked up to the same battery, right? So the voltage between these two spots is going to be the voltage between these two spots, voltage between these two spots, and the same thing there. So our voltages are going to be equal. What about the currents? Are these going to be equal, or are you going to add them? Add them. And I like that because whatever current's going through here is not necessarily the currents that are going to go through the other branch. So first off, you absolutely cannot say that these things are equal. There's a possibility that they might be equal, but I1, unless L1 equals L2, I1 does not equal I2. And you would expect these things to add together to some overall current. Okay, so let's figure out what we're going to do with that. So again, sorry, it'll take me a second to write this down. I1 plus I2 equals I equivalent, and V1 equals V2 equals V equivalent. Okay, that's nice. Okay, going here, I definitely want to relate current to current to that thing again. Man, I've lost it. Current to inductance, clearly. Okay, I want to, relate current to inductance. I don't like any of those. What else might we have? Okay. Okay, what if we started there and did the trick that we did before? Where if this is true, certainly we could take the derivatives of this whole thing, right? We could say d I1 dt plus d I2 dt equals d IQ dt. And now going back to here, I can say di dt equals the voltage over the inductance. Sound okay? Okay, cool. And that's how we're gonna kind of shoehorn our inductance into this. So V1 over L1 plus V2 over L2 equals V equivalent over L equivalent. And what can you guys tell me about V1, V2, and V equivalent? They're all equal to each other. Excellent. So we end up with 1 over L1 plus 1 over L2 equals 1 over L equivalent. Which is great because that's what we should have, right? That's what if we said that we were just saying L1 plus L2 worked for series, then we probably should have 1 over L1 plus 1 over L2 for parallel. So that's how you add inductors in parallel. Awesome. We'll come back. We will do a few more problems on Thursday, and especially in terms of energy, and then we're going to do an LC circuit, which is actually super exciting. So I'll see you Thursday. Great. Online people, are you okay? Hopefully. Okay. See you guys Thursday too.